Hello, I am Michael Mogensen, and this is Async Scripting with Lua and libuv. This talk is really going to be a series of demos that combine scripting, networking, event-driven programming, all for an embedded target. We'll go in order of increasing capability, complexity, and usefulness. There will be two parts. The first will be blinking an LED in 3 different ways, and the second will focus on networking. For these examples, I'm using an Odroid Go. This is a little handheld game system. It's meant to emulate retro video games, but it has an ESP32 inside of it, as well as a battery and an SD card for a permanent file system. There's no hardware dependencies for the stuff I'm going to show. Any NuttX target that has networking support will work just fine. Lastly, I did this for personal projects, so everything here may not be production ready. And I want to stress one point: the vast majority of the work that I'm going to show today is from other people. So credit to the original authors, and let's get started. All right, so first, what is Lua? Lua is a relatively popular scripting language. It runs in a stack-based VM. There's kind of one rule in Lua, and that's everything is a table. So a table is a dictionary or hash map, and it's used for an array, which is a dictionary that has consecutive integer keys. It's used for classes, where a table has names for keys, and then has class variables or class methods for values. And it's pretty easy to embed in an application. There's a C API for calling from Lua to C, and also from C to Lua. We'll look at extending Lua in NuttX with some C modules to get access to hardware in just a bit. It's pretty easy to port to a new system. Its only dependency to build is libc. And I should note that there have been a ton of people who have built Lua for NuttX before, and there will be a ton of people in the future. Big shout out to another talk that's happening this weekend about porting a different flavor of Lua called Lua JIT for just in time to a platform for NuttX. That's really cool. The one we'll be using as of this year, Lua has been added into the NuttX app repo, so it's available under the interpreters directory, and it comes with some nice build hooks. All right, so let's switch over to my serial terminal here and just check out the Lua REPL. Launched out with Lua. We get some stuff. We could do things like print hello. Close out of it. Take a look at our file system here. We have a file called Hello Lua. So Lua has a module system. Modules are just other Lua tables that happen to implement certain functions. So here we create a table called hello. We add a function to this table called say hello, and then we return this table from this file. And so if I start my Lua REPL again, I can do require, which is the same as Python's import statement. Now I have this table in my REPL. I can call that function. And that's how we share Lua code in between different files. All right, so it's fun to print stuff, but it'd be great if we could access some hardware. We can do this by extending some Lua with some C modules. So NuttX has a user LEDs driver. This exposes a character driver in a pseudo file system, and then uses an IO control that lets you request a certain LED state. Since Lua is built just on libc, doesn't have any knowledge of an IO controller, what that is, but we can build a C module that's just a very slim wrapper over the IO control function. And that's what I've done here. We'll have Lua pass the file descriptor, the IO control request, and any parameters. C will call that IO control function and then returning results. And then in order to use that in our program, when we load this C module, it'll go and look up the Lua's file type. And this file type is just a table. It's got a bunch of different methods as members. And so we'll add our IO control method just right at the end. And in order to get the C module into our Lua environment here on our board, we'll use part of the Lua interpreter in NuttX apps. Has a module makefile. And similar to registering a NSH app, in the makefile for our C module, we can just include this Lua module, and it will add it to a registry, and then it will insert it into our Lua environment that we start up on our board. So let's take a look at a file called io-control.lua. All right, so down here, we print some stuff. We use some standard file operations to open dev user LEDs. We start a for loop here. Our LEDs file right here, our file type, has an IO control method. And then we pass it with the specific IO control request. We pull these right out of the NuttX C header. Second parameter is which LED. 0 is first one, and then the last parameter is the state, true for on, false for off. And then we're not doing any threading or anything here, so we need a way to have a block-in wait delay. And we can do this by doing os execute, which shells out to the NSH shell, and we'll call the command sleep1. So let's run this. And then press enter. All right, and got an LED blinking. All right, let's get a little more advanced in our LED blinking. All right, one great feature of Lua that's built in are coroutines. So coroutines are a form of asynchronous cooperative multitasking. Like I mentioned, it's nice that they're built into Lua. No external library needed. So the actions you can take on a coroutine are you can yield data from it, you can resume a suspended coroutine, and you can wrap a coroutine into a top-level blocking function that will drive it to completion. So this is relatively similar to Python's async await and asyncio.run methods and syntax. Coroutines are nice because you can convert callback code into synchronous top-to-bottom flowing code. And one thing Lua is missing is some sort of non-blocking async IO. So there's a library called libuv. There's a C library that provides asynchronous IO using event loops. It gives us things like timers, networking, file IO, IPC, and signaling. It's relatively battle tested. It's used as part of the core of the Node.js project and the Julia programming language. And best of all, it's already been ported to NuttX. So it's available by default in NuttX apps system. And then to use this library from Lua, someone else has also already written Lua bindings into libuv. This is via C module. And so we can just drop this into our NuttX project. It builds without any modification for NuttX. It just requires libuv. And if we include our Lua module makefile, this will be available in our Lua environment. As an aside, I think this is what makes NuttX really great. So there are these amazing projects and libraries that are out there, and we can very easily just grab them, stitch them together, and build something that's greater than some of its parts, but for an embedded target. So let's take a look at this. All right, first let's look at love.lua. So this example, start off relatively the same. Open our LEDs file. Now we got a timer variable that is a libuv timer, and then a global state tracking variable. And then we take our timer and we start it for 1,000 milliseconds in the future and tell it to repeat every 1,000 milliseconds. And when this timer triggers, it'll call a callback function. This is an inline lambda style callback function. And then we invoke an IO control method, toggle our LED state. And this run method down here will invoke the libuv event loop, and we'll run from there. So do this. No real change from application level, still blinking. Now we are in a callback event-driven base design. And then to take it to the next step, let's look at how we can convert that callback code to synchronous code using coroutines. Check out Koru. All right, we're going to start down here in the middle. All right, so we have this method coroutine wraps. So we'll take this coroutine function that we're defining in line. It starts by opening LED drive, LED file. Then now we have a for loop. We can go top to bottom. We toggle our LEDs, and then we need a way to sleep or to delay, but delay in a non-blocking manner. So we want to yield from our coroutine. So we have a function here called sleep, which is defined up here, and we do something a little bit clever where we take our currently running coroutine, we capture it here, create a timer, start a timer that will resume our coroutine, and then down here before our timer expires, we will yield our coroutine, which will put it in the suspended state. So we have a way to wake ourselves up in the future based on a callback. So this works the same way that Python's async IO sleep does. If we run it, I think you can guess what will happen now. That is the same Blinky. All right. Let's move on and talk about networking. Because I think one of the best things we get from libuv is networking support, specifically sockets. So libuv sockets follow the normal sort of BSD socket API. You can create a server. So if you wanted to create a TCP server, you could create a server socket, then call bind on it, then call listen, and then when a connection occurs, you can create a TCP client socket, then call accept, and then exchange any data. And this happens the same way, but in the background, libuv is using select to wait for each socket to get to the desired next state, and then invoke a callback up to Lua to take whatever action is needed. So let's go down here and let's look at a TCP echo server that I made. All right, let's start up here. We have a little helper function called create server. Host takes a host port and an on connection method. So create a TCP server function, call bind, call listen, and then when listen has a connection, it'll call a callback defined here. So create a client socket, then accept it, and then we'll trigger this on connection method to run. And we'll use that helper function down here to create a server, let libuv choose what port to use. And this is our on connection method. So we'll have our client here, and now we can read a chunk of data. So if we get the chunk of data, write it back to echo. If not, close the socket. So let's fire this guy up. Okay, let's see. This is print listening on this port. I'm gonna pull up another terminal here. Right, okay, that's my board's IP address, and then we need to connect to port. All right, now if I type something, it should be echoed back. Great. All right, so what can we do with sockets? We can use them for an HTTP web server. All right, and like everything else I've done so far, instead of writing my own web server, I can take a web server that somebody else has already written for Lua and just run it on my embedded board. So there happens to be a web server project called Atlas. Its dependencies are Lua and libuv, and uses love as the Lua module to access libuv. So we have everything we need. This particular web server spawns coroutines to handle each HTTP request, so that we're not going to block a new connection by waiting to read data from a socket. We'll just handle it as it comes. This is more than just a web server. This is organized into a web framework architecture. So similar to Django from Python, we have a separate web app from the server. And then this web app registers controllers for certain routes. So, you know, slash index.html versus slash my other page will be different routes. And in this context, a controller is simply a function that receives a request table with a bunch of details about the request and the client. And its job is to return a response table that has HTML content or an HTTP status code or any other data that you want to return. And then the web framework will take care of the actual transport. So let's take a look at what we have here. So my file system here, I have an app directory. So we look at app.lua. There's a lot going on here. Let's scoot this guy over a little bit. All right, we're gonna go quickly just bottom to top. All right, so we have an app variable here. It's type application, takes routes. We got 3 different routes here. We got /on that's registered with controllers.on, off for controllers.off, and then sort of a home default one for controllers home. Up here we have our controllers. So these are just named functions. So on is a function defined as this inline function that takes a request, turns a response. The response is the result of this other function LED with parameter true, and give it a little hint that it's of type plain text. All right, similar thing for off, and then home here returns the result of the home function, and we assume it's HTML. And if we look up here for the home function, we start off by collecting some data from our Lua environment and our NuttX platform. We have some links here. So we generate some HTML content on the fly. And so, you know, we could change this HTML content based on some parameter of the request to, you know, give you a different web page than you would give me if I requested. And then our LED function looks pretty familiar by now. Open our LED file and then use IO control to set a desired state. And then to invoke this, let's look at, we have our start server file. And so this guy down here creates a configuration that registers or that uses our web app and this somewhat confusing notation, which is tells Lua, look in the app directory for a file named app.lua, and in that file there'll be a variable named app. But gets us where we need to go. And then finally, to start things off, we have our coroutine wrap function, which takes our top level coroutine, which is the coroutine that all the other generated or child coroutines can then yield back to, and then starts up our server and then waits for connections. So let's give this one a go. All right, we're listening here. I'm going to pull over our web browser. And let's get the IP address for our board. So we should be able to go to board's IP address. All right. So we get some information like the version of NuttX we're running. Pull out some runtime information like how much memory the Lua VM is currently using. Let's see, it's a bit under 100 kilobytes. I don't have much of a benchmark, but that seems pretty reasonable to me for running a completely interpreted language inside a VM. Then we have some links that we have. So if we go to on, we set our LED on, and then if we go back, set it off, we can control the state of this LED remotely. All right, so why might this be neat? We're running this this web server, and we didn't have to reflash our board in order to run any of these demos. In fact, I never even had to reboot my board. So we could take this web server and we could have the user copy a new Lua script to an SD card, stick it in a board, or we could programmatically fetch a new Lua script from a remote server somewhere. We could, modify our web app on our board to add a new route to control a different piece of hardware in a different manner. We could do this without having to modify the core NuttX image. And if we wanted to accept some code from the user, we can run this in a Lua environment, and you can modify the Lua environment. You can do things like create a sandbox by removing modules and removing functions. So you can remove the IO module, and then this user executed code can't access the file system at all. That's why I think it may be worth looking into scripting language and Lua as a scripting language for your next NuttX project. So let me drag this down. Let's go back. All right, finish up. All right, thank you for watching. That's what I have for today. All the links to the demos I showed and C modules, other people's projects can be found in the articles that are about the same topic at medium.com. The link's down there. All right, thank you very much. Take care.